Hi everyone. I've just seen that there's quite a few attendees joined. I think we're good to go from the joining front. Just to give you an overview, we've got a few introductory slides to make where we'll introduce ourselves, the company, the topic that we're actually going to go through today, and then we'll actually get into the nuts and bolts of things where we'll talk about the SimScale platform, how to obtain results, and how to set things up. So without further ado, my name is Darren Lynch. I'm a CFD application engineer here at SimScale. I've got experience in CFD and engineering design, and I graduated in aerospace engineering at Brunel University. As I said, I'm part of the application engineering team, and I'm partnered with Nagman, my colleague, who I'm going to pass over to introduce himself to next.
Hello everyone, my name is Dr. Nagman Khan. I'd like to welcome you to this webinar. Hope everyone's safe and well. I'm an account manager here at SimScale, and I have a background and PhD in building simulation. So we're combining Darren's expertise in aerodynamics and my expertise in building simulation to bring you some really great insights today.
Thanks, Nagman. So first up, SimScale, who are we? So we were founded in 2012, and we grew out of the office in Munich. And since then, we've expanded into Boston, New York, and Nagman and myself are based in the UK, hence the little dot there. We've got 80 plus employees and expanding all the time, and we cover 6 different time zones, which means, quite frankly, our support level is quite world class. We've got 150,000 users worldwide, and we've got more than 300,000 simulation projects, which means that there's a lot of expertise on the SimScale platform that you've just got access to just by logging in. What we do, we offer a platform that's completely on the cloud. We access the SimScale platform, as you can see on the left there, straight through the browser, and we offer different simulation tools such as computational fluid dynamics, solid mechanics, and thermodynamics. And the one we're actually talking about today will be based on the fluid dynamics part of the software. So today's topic is wind pressure coefficients. We're going to talk to you about why they're important, what they're used for, and later on we'll actually talk about how we can use SimScale to obtain these pressure coefficients more accurately. In the next couple of slides, my colleague Nagman is going to talk to you more in detail about what they're used for, what they actually mean, and also straight after that, we'll move on to how they're actually defined. So Nagman, I've got a few slides for you.
Thank you, Darren. Okay, so why are wind pressure coefficients so important? Well, I mean, the wind pressure is an opening. The wind pressure at the opening, and hence delta P, really influences the building design. Okay, so Darren, if you just skip through the bullet points.
Sure.
So what we can see here, that fresh air and air exchanges are all influenced by wind pressure coefficients.
So when we're actually setting up some of these problems, we're interested mainly in the change in pressure. So these changes in pressure can affect the flow rates going through space. They can then affect the temperature difference between the building and the external of that building. And these are all going to affect various things in your building design. So for example, if you've got an inaccurate pressure difference defined, then this is going to affect the air change rates and also the air flow rate going through. And of course, these have a knock-on effect with things like the temperature, the thermal comfort, and the energy costs that are actually going to be involved with heating and maintaining a building. So why are wind pressure coefficients so important? Let me just skip through the animations here.
Darren, I'm back. Sorry about that technical issue.
Problem.
Can you hear me? Thanks for jumping in there. Yes, thank you so much. So what we're saying here is that PW is your wind pressure, which is dependent on your wind pressure coefficient, which is CP. So if you look on the right, you can see a basic equation which defines wind pressure equals CP half rho V squared. Now, rho is your density of the air, V is the reference wind speed or wind speed velocity at your opening or building height. And you can see that Cp is a critical value here. Okay, so Pw, the wind pressure, is then used to calculate the delta P, which is the difference in pressure between the inside and outside of your building. So imagine you have an open window, there's a pressure outside, there's a pressure inside. That delta P then will drive the flow rate through your building, right? Through your doors, your louvers, your grills, your ducts, your doors, whatever kind of opening you have. So then the delta P is used to calculate your mass flow rate exchange between the inside and outside of the building, right? And obviously there's temperature differences. Obviously your inside of your building is at room temperature and the outside temperature varies, throughout the year, every hour, if you're using a dynamic weather file, for if you're doing kind of thermal modeling. And what that means is that there's not just a delta P, there's a delta T, okay? So this delta P then is used to calculate how much air is exchanged into and out of the building. And if you're using building simulation software tools, the common ones we use are things like Design Builder, TAS, IES. They will basically have a very simple bulk airflow network model, which just uses simplified relationships for wind pressure coefficient to then calculate the wind pressure on your opening, and then to calculate your delta P between the inside and outside of your building, which is then used to calculate the mass flow coming into and out of the building. Okay, so if you imagine the mass flow rate and the delta T, the difference in temperature, is then really directly linked to the calculation of your heating load and your cooling load. Okay, obviously, if you're bringing in cooler air from the outside, that's going to impact your heating load. And if you're bringing in warm air from the outside, that's going to impact your cooling load. So that means this has a direct consequence to overall energy, kilowatt hours, and hence cost, right? Your electricity, gas costs. And it also impacts your thermal comfort. If you're trying to keep your inside temperature to a certain thermal comfort band, really what's driving that, a lot of what's driving that natural ventilation and ventilation flow is the external environment, right? And we don't really consider this. Why? Because we cannot consider this in thermal modeling tools, because they're not really designed to do it. They don't have that CFD capability to do it. So the overall zone and building energy balance is then heavily influenced by the CP, the wind pressure coefficients and wind pressures, okay? And this impacts on air velocities in rooms for comfort purposes as well. Now, just look at that equation again on the right-hand side. You can see Pw, which is the wind pressure, equals Cp, which is the pressure coefficient, multiplied by various other variables and constant. Just imagine if there was a 50% error in your Cp value. Your Cp is the wind pressure coefficient, okay? So imagine that Cp is off by 50%. Imagine then how that error propagates through all of the above. That 50% error will cause an error then in the calculation of wind pressure, which will cause an error in delta P, the difference between internal and external pressures, which will cause an error in your airflow coming in and out of the building, which will then directly impact your heating load, your cooling load, your overall energy, the cost, the thermal comfort, and the overall building energy balance. So CP actually is really, really critical. And one of the reasons we're focusing on this is that the traditional building simulation tools do not really account for this in any accurate way. And if we go on to the next slide, please, Darren.
Sure.
What other factors should you watch out for? So again, most thermal modeling and building simulation tools use very simple airflow network models to calculate bulk air movement. They do not capture the following effects, okay, in any real accurate way. So they won't account for wind turbulence. And obviously, if you're modeling buildings in dense urban areas, in cities, in populated areas, wind turbulence is a huge, huge issue. Okay, they don't also model external wind conditions properly, or the local building contexts, right? They will use basic wind speed, wind direction, and that's it. But obviously, if you have a building next to you or lots of buildings next to you, there's very limited treatment to that. There's very limited ways you can correct for that. Also, terrain is an oversimplified constant in these building simulation software tools. Just going back to the local building context, in these tools, you have something called exposure types. For example, there'll be, if you have a building facade, you might have the option to categorize that as either open, sheltered, exposed, semi-exposed, various different things. And that will then add some kind of correction or constant. But these are very poorly understood and very poorly applied, we find, in building simulation applications. And they're also based on very simplified wind tunnel testing that was conducted a long time ago. So I think the question we're really asking here is, have you ever thought of how your wind pressure coefficients can be more accurately calculated? And that's the purpose of today. And I will hand back to Darren to show you how that can be done.
Thank you very much, Nagman. So yeah, exactly what Nagman said. How can we then go and obtain a more accurate pressure coefficient for you to use in your thermal modeling? And we've got a three-part workflow here at SimScale where we can basically guide you through how to get these pressure coefficients. So the first step is obviously to run a CFD simulation. And we're going to go into that in detail, but actually it's quite simple, especially on our pedestrian wind comfort analysis tool. Then what we're going to do is we're going to take those results, we'll take the pressure results, and we're going to convert them using the equation that Nagman showed earlier into pressure coefficients. And then what we can do is we can simply query on the surface of your building what these pressure coefficients are going to be and input them back into your model. And we can go into a little bit more detail. So the CFD setup and process is very simple. It's a 3-step process, and we're going to go and show you that. Basically, a simulation can be set up and run within 10 minutes in most cases, which is incredibly fast, and you can get results probably in under an hour. The pressure coefficient calculation, here is the famous equation again, except this time it's rearranged. So we've got the pressure coefficient is the subject, and we're going to say that actually the velocity or the speed is that is applied at the relative height in the atmospheric boundary layer. And this atmospheric boundary layer might change depending on what environment you're in. So you might be in an urban environment, you might be in an open rural environment. And you can adjust these in SimScale, and likewise you can adjust the relative pressure, relative velocities in your post-processing. And out of all this, we get a CP field, a pressure coefficient field. And to give you an idea of what that looks like, it looks very similar to this. But how can we query that? Well, it's actually quite simple. Once you've gone through and done the calculation based on pressure, then you can just click on whatever point you want to analyze, and it's going to annotate to you a pressure coefficient. And these can be then brought back in to your thermal model and used for more accurate modeling. So I said that I was going to briefly take you through the simulation setup. We do pride ourselves in the fact that it's very fast and easy workflow. And actually, to show you how fast and easy it is, I'm actually going to show you the SimScale platform straight after this these slides. So in a nutshell, 3-step process, as I said. You would define the region that you're interested in, define the windrows in which you actually want to apply these simulations, and then you would define a pedestrian zone. Now, the reason for the last step is because we're actually doing a pedestrian wind comfort analysis, although we're using the pressure results rather than the pedestrian results. I think I defined it quite easily. The windrows in this case is normally used for pedestrian results, but in this case we're only using it to define the directions. And the pedestrian region is actually an offset floor, although we're not actually going to be using it in this simulation. And to show you exactly what I mean, we're going to do a live demonstration. So hopefully you'll be able to see my my screen. It should be a SimScale platform now. Nagman, can you just confirm?
Yes, that's right. I can see it.
Great, thank you. So in the SimScale platform, you can see that we've got it open. It's in a browser, and we've got a geometry. It's quite familiar to some of you, I'm sure. This is the walkie-talkie building. Surrounding it is the context in which we're applying, and also a terrain surrounding it as well. And when we start to set up the simulation, we're just going to go create pedestrian wind comfort simulation, and we can actually do that right now and show you how fast and easy it is. So by default, it's selected our geometry to be used. Region of interest, automatically it picks up the center of the simulation, and we can just change and reduce that region of interest. We can tell it what directions we want to run. So what weather data do we actually want to use? And we could just type in London, London, here we go. And in this case, I've just used an import weather data from our connected provider, MetroBlue, and it's defined for us. For this demonstration, we just used 8 wind directions. So that's 8 different wind directions that we're going to obtain results for. And then we can query the pressure coefficients on all 4 faces for every single direction. And this is basically the extent of the simulation setup. The only other additional thing we need to do is just click on that face there, just to satisfy minimum requirements. But we're also going to say that we're going to export statistical results on the surface around this building. And that's exactly what we've done in this simulation setup. Hopefully that gives you an idea of how fast one of these simulations can be set up. It took us, a couple of minutes right there. And then to run a simulation, we just hit run, and we get results in, let's say, 214 minutes in this case. So live demonstration over, back to the results. What are we going to get out of this? So firstly, we're going to say straight up front that you can do this yourself today on the SimScale platform. We're providing you here an example project, which is this walkie-talkie building. In there is all of your pressure data, and you can download those results. And also, I've provided a PowerView state file. Now, all you then have to do is load the state file, and it should just run. And these results will just come out. So, what have we been able to obtain from this simulation? Well, as I mentioned before, it was 8 different directions, all at the same time, and it took less than a couple of hours. Results were exported on all of the surfaces of the building, which means for every single one of those 8 directions, we've got pressure results and we've got pressure coefficients. So if we wanted to query the face at 0 degrees angle of attack for the easterly direction, then we can just probe a point on that surface. And they look something like this. And as you can see, in the center of the building, you've got a pretty constant pressure coefficient, drops off towards the top, drops off towards the bottom. And what we're actually going to show you is the pattern, but on a more interesting side. Let's use this view just to give it a bit of context. So you've got buildings behind it on the side, and these are all going to affect the pressure on these surfaces. We cannot say that they're going to affect it in a certain way, because quite honestly, there's so many variables here, so many complex flow phenomena that we couldn't possibly account for all of these. And that is the problem that we're highlighting and the problem that we're hoping to solve. So on the next slide, we're going to show you actually how we're going to show you that. So we just looked at this front face on a southerly direction. And now what we're going to be doing is looking at the wind from an easterly direction. Interestingly, on this front face at 0 angles of attack, we've got a building directly next to the bottom of the building. And you can see that although the pressure coefficient is fairly constant throughout this face, actually below the point of the surrounding building's height is going to be actually a lot lower. And you can see it quickly gradients into a lower pressure coefficient. And this is the kind of thing that we would try and predict and try to factor in when we're doing this analytically. But very rarely can we actually get this spot on. And we would rely in that case on an almost perfect idyllic case where we would have a very strict context and also a very uniform building, i.e. a tall, slender building. But in this case, we've got neither. We've got very complicated context. We've got tall buildings close. We've got tall buildings far. We've got short buildings surrounding it everywhere. And we couldn't possibly account for all of this when inputting this into a thermal model. But CFD allows you to do that. And for every single direction, it's going to calculate the flows. It's going to calculate the pressure coefficients very accurately for every single direction. And to really illustrate how this is shown, we can compare what we would get in a thermal model. And Nagman, feel free to chime in on this slide.
Yeah.
What we can see is quite a difference, certainly in the top part of the building, where the flow is moving over the context, and it's going to be much faster. However, where it's shielded below the height of that surrounding building, you've actually got a much lower pressure coefficient than you would get predicted for the thermal model. And I've illustrated the building height with this red line here.
Yeah, if we look at this in the context of what I was talking about earlier, this is critical, and I don't think this is something we really talk about enough. Okay, and I can see some familiar names on the attendee list, so a lot of people will know what I'm talking about. When you're modeling a building in a thermal model, like TAS designed by the IES, for example, people will take a lot of time to set up the internal conditions of a building, right? So we will focus a long time and effort on internal gains, as well. You should as well. In internal gains, the fabric, the U values, what kind of equipment we're using, profiles, schedules, all of this stuff, the plant, the HVAC equipment, and that's fantastic, and we should do that. But what we're doing is not treating a really critical component, right? We're not coupling the external to the internal environment when it comes to wind and air movement, and this is critical. So we do with solar and thermal. So U values, will spend a lot of time on that. Glazing, will spend a lot of time on that. The treatment of solar gains, people will spend a lot of time trying to do that. But when it comes to wind, for some reason, there's a big gap. It's not treated very well, very academically at all. And what we do is, for some reason, we're just happy to accept these kind of standard wind pressure coefficients that we've had for ages. No one really questions them. But here's a really great example of why that can't continue to happen. So let's just elaborate on this chart a bit more. Okay, there's a lot going on here. So on the x-axis, we have the wind pressure coefficient. So this is the CP that we were talking about earlier, okay? And we've plotted two sets of data here. One is, if you look at the legend at the bottom, the CP from a thermal model, which is the square icon, okay? So here you can see there's 1, 2, 3, 4, 5, 6 black squares, the unshaded black squares, which is the series thermal model CP. So that is a wind pressure coefficient you will get from modeling this exact building with its height, its facade, its orientation, the angle attack of the wind from the thermal models that you use normally in thermal simulation and compliance and for calculating energy, etc. Okay, the blue line is the wind pressure coefficient, the CP, that SimScale has calculated for the exact same building. Okay, the same building, the same angle of attack on the same facade with the context now taken into account, with the turbulence taking into account, etc., etc. Okay, and you can see on the y-axis, this is the height of the building. This is a ratio of height of the building. Okay, so the small h is the point on the building where we're taking a reading. So imagine that's, let's say, an opening height, let's say window. Okay, and then the big H is the height, the whole height of the building. So small h over big H is just a number like 0.2, 0.4, 0.6, 0.81, and these standard thermal model wind pressure coefficients are given for these values 0.2, 0.4, etc. up to 1 for different angles of attack, different exposure types. So we've taken those data and we've plotted them here, okay, which are the black squares, and then we're plotting the blue line, which is the calculation of the wind pressure coefficients from SimScale. Now, what's interesting is that the shape of the curve is similar. Okay, if you compare the black squares to the blue line, the shape is vaguely similar. Yeah, we can see the same kind of behavior, the relationship, the curve, and that's fine. That's a great thing. Okay, but the values, the absolute values, you can see it's ridiculous. They're changing in value by 100%. So remember earlier I asked you, imagine if there was a 50% error in your CP value, how would that propagate through the rest of your building design? Here, clearly, we're seeing 100% error, okay? And this is what this graph is trying to show for this particular example. And it's not just this example, we see this all the time, right? This pretty much happens on every building. And unless you're really going into detail about trying to model the wind pressure coefficients in detail in your thermal modeling tools, you will always have this. Now think about, let's discuss in the summary section. I'll hand back to Darren for this bit, but in the summary section, let's discuss what impact that has and what we can do about it. And if you have any questions on this, please keep sending the questions through the GoToWebinar.
Excellent, thank you. Yeah, and just to iterate on what Nagman just said, I've seen quite a few coming in. I think what we'll do is at the end, when we have our question and answers, to make sure that everybody knows the answers to the questions you're asking, we'll go out and read through a few of those. So the summary section, we're just going to give you an overview of everything that we've discussed up until this point. And Nagman, do you want to do any of these points, or should I just run through it?
Yeah, no, I'll start and then just jump in wherever you want to add anything. So, this is critical that we understand this, and our industry understands what's going on. So, what we're talking about is when you're comparing pressure coefficients. So, we're talking about wind pressure coefficients on your building facades, right, at your building openings. Obtaining building simulation models, we see the following. So, Darren's already shown the behavior. So pressure higher up the building is much higher in comparison to the standard methods, where flow is much faster than expected for the wind profile due to upstream obstruction. Why is this really important? First of all, we design a lot of tall buildings. We're designing cities, complex cities. We're going higher and higher, not just commercial buildings, but domestic as well. If you think about residential buildings are getting taller and taller in the big cities. This is really important. Those buildings suffer from overheating, right? You have small compartments, apartments rather, crammed into these tall residential buildings, and we're counting on ways to avoid overheating. We can't afford cooling, right? And mechanical ventilation, yes, is an option. And everyone has windows, right? So we're supposed to be using natural ventilation. In the UK, we have standards like TM59, which talks more about how we can do that and how to account for window opening, ventilation, thermal comfort. But what's the point in all of that if you're not really capturing the flow properly of outside to inside? This is actually a critical thing, right? So this point is super important. The next point, lower down, it's much less as surrounding buildings are actively obstructing the flow. And this brings us up to turbulence. If you have lower down in the building, kind of ground floor and close by, there's a lot of buildings of similar height around that area. Okay, and all of that, and it's not just the buildings, it's things like the streets, so urban canyons. And imagine the turbulence. You've got transport, traffic moving past. All of these things will have a major impact on the wind pressure field around your facade and building. And again, that's not really being captured in the architecture, engineering, construction industry at all. And it's shocking because it's really easy to do. Darren, my colleague Darren, just shown you a way where in a transient way you can account for this, model it, set it up in a few minutes, get results in about an hour, and use those CP values then to enhance your building design and connect it with other third-party tools. So it's really surprising to me that this doesn't happen more, and that's something we're interested in discussing with you. If you've got projects on right now where you want to do this in a bit more detail, talk to us. We've got contact details at the end, and let's see how we can help you do that. Okay, the third bullet point there. Up to 100% difference in CP values across the length and width of the building. Okay, 100%. So remember at the beginning, I said, imagine if you have a 50% error in your CP value, how is that error going to propagate through to impacting on the calculation of your flow rate? Okay, so imagine your fresh air flow rate. Are you actually meeting the minimum ventilation requirements, right? You might have, for example, 10 liters per second per person and you're counting on that from a lot of that from natural ventilation. What about CO2 and air quality in your building? If your thermal model is saying that, yeah, by natural ventilation, you can meet 50 to 60% of that air quality just by window openings or louvers or grills, that's not accurate at all, because you're not calculating the wind pressure coefficients properly. So your fresh air rates, air quality, and these are compliance requirements. So you're not complying actually to the law and the building regulations if you're not doing this properly. It's not just design, this is compliance with your building regulations. Okay, imagine that error propagating through to calculating airflow rates, loads as well, and comfort. So all of that then impacts your cooling loads, heating loads, and energy, as we talked about before, and your thermal comfort. We all know the velocity of air in your room will impact your thermal comfort, and it's a variable in the calculation of things like operative temperature and various other thermal comfort criteria as well. And sometimes we're given a value to use when it comes to compliance or overheating assessments, but how can you actually see that? Also, what if you have an open window? You want to know how much airflow is coming through in reality, right, based on the outside wind conditions, and also see the seasonal pattern maybe, right? So instead of having an annual approach to this, you might want to break it down and see what the seasonal impacts are. So the question on the top right then is, how will this impact your overheating assessments, your fresh air rates, your energy loads, and your compliance? It's very important. Again, my takeaway from this is a couple of key points. One is that we're not calculating wind pressure coefficients properly, and they're not being accounted for properly in our building simulation thermal models. The follow-on point logically from that is that there's a huge error when we calculate our fresh air rates, our ventilation, our thermal comfort, our heating, cooling loads, and hence energy. So there's one small value like wind pressure coefficient will have a huge impact on your overall building design. Yep. Okay, Darren.
Excellent, thank you. So that concludes the slides. Dagman, I'm going to move on to some questions and answers, and I've seen quite a few questions actually coming up. So what we're going to do is hopefully read out a few that have been answered, and also address some that are just coming in that haven't been answered yet. So I think the first one I'd like to address is how do we know that these CP values coming from both models are correct? Our validation is done. Well, obviously I can only account for SimScale side, in which case we do have validation models for this full fresh coefficients, and they actually do correspond quite well.
And that's an interesting question. So Darren, you've answered it from SimScale's perspective. I'll I guess give the other view from the thermal modeling perspective. I guess so. If you look at the thermal models, the building simulation tools, and how they use CP values, these were a lot of the values were done on have come from wind tunnel testing that was done a long time ago. Right, and wind tunnel testing, as you know, is highly simplified. It's mostly designed to capture, the behavior of the flow around your building, and that data was then used to basically this other software vendors have taken that data and they've interpolated it and they've extrapolated it to apply to any building. Right, so there's inherent errors there. It doesn't also account for turbulence, the context properly, as we said. And the corrections that they suggest, like exposure types, are poorly understood. So I think the original study, the original set of studies, which was done a long time ago, where this data has come from, yes, that study was a great academic study, but the application of that study and extrapolating and interpolating it to more and more complex building projects, facades, interactions, etc., I'm not sure how well that is validated, right? And all you need to do is just run a few comparisons yourself, either in the simulation tool or in SimScale, or perhaps both, and see what the differences are. And that will tell you the kind of errors. We've done this a lot internally. We can see, huge differences in CP values.
Excellent, thank you, Nathan. Hopefully that answers that question. The next one was, how do we know that those CP values? What about the mesh independence of this model? So of course we've done the validation and we know approximately at these city scales where the mesh finers should be and what they should be, and we based upon those. Of course, if you're going to do your own project, then you need to do your own mesh independent studies because it will always be different from case to case. And we do show a mesh independence in the validation case as well. Quite a few other questions popping up. Let me just read out a few of the previous ones. I'm not sure if everyone can see the results that have been read out. One of them was wind should be obstructed by some other buildings. Yeah, we've shown that these CFD results were actually obstructed by other buildings, and the results take that into account. Is the approach also applicable to finding pressure coefficients to calculate structural wind loads on the buildings? Yes, absolutely. You can reach out to us and we can actually share with you some instructions on how to do that. But once again, that's very applicable to that validation case as well. What will be the probable difference between the wind tunnel to this and the CFD analysis? Providing we follow all the best practices, then actually they would be very, very close. Probably under 10% if you did the mesh independent study. Is the building modelled as a rigid obstacle, or is the building flexible and captured through fluid structure interface? SimScale doesn't support fluid structure interface at the moment, so this is completely rigid, and obviously we're not taking any fluctuations in terms of building movement into account. So we've done a transient analysis on a rigid structure, and we've averaged the results over time to obtain these average results. Another question was, are these steady state results or transient? Just to clarify here, this is the SimScale's pride. This is the lattice Boltzmann solver. It is transient. We've obtained these average results by averaging over time. And all these transient results were run with a turbulence model called K omega SST delay detached eddy simulation, which is a hybrid model and highly regarded as a very accurate one.
There's a question on the context and where that comes from. Is it manual? I think it's probably worth talking because the context is so important for wind pressure. Do you want to just comment on that?
Of course, yes. So the context is brought in with the geometry in this case. So we actually use a software called CAD Mapper, and they provide geometry basically from a mapping service. So all I did here was upload all of that context with a more detailed model for the walkie-talkie. We support a lot of different CAD formats, and I know that there's a lot of different sources for the context. So these might come from many different sources. You might even decide to do a point cloud and then do some meshing based upon that. Generally speaking, everything comes up to SimScale. One of the most compatible formats is the STL format. So if you can get it in STL, SimScale can probably take it. So I've got another one. How can you model vortex shedding? So we've got this model. We can obviously analyze vortex shedding off of the rigid body. Obviously, some buildings will be influenced to some degree by that shedding and therefore make them wobble, but that is not taken into account. However, you can absolutely export slices that show the velocity slices, and you can see there the vortex is forming behind that building. That can be done either on the pedestrian wind comfort analysis, but if you just want to see one direction, then you might just want to do that on the lattice Boltzmann solver that we can provide for you. Obviously, vortex shedding is naturally a transient phenomenon, so you will need either the lattice Boltzmann solver or the pedestrian wind comfort analysis for that. So if you're a community user or you haven't got a professional account with us, then maybe reach out to Nagman and he can point you in the right direction for that.
Okay, Will, this is Nagman here. I'm still here. We'll take a couple more questions. I think we've got a few more coming in here. I'll just wait for my colleague Darren to jump back on. So there's one question: how can one account for internal pressures, CPI? So this is basically at the heart of it, SimScale is a CFD tool. So there's various boundary conditions that can help you to set up the internal pressures. If you had openings as well, that's totally possible. This seminar was focusing more on the external wind pressures on the facade, which would really drive the airflow through a building. So the CP value you get from here, some of the outputs that we've been showing you on these slides, is used to then you could export that and import that into a third-party tool, like a thermal modeling tool or a building simulation tool. So that was a key thing from this takeaway. But certainly there's other more detailed analysis we can do when it comes to pressures. And also, if you had projects going on right now, or they're about to start, for example, and you've never really looked at wind pressure coefficients in any detail, or a bit more, you're interested in more of a complex treatment of the coupling between the external and internal environment, and especially if you're using that with trying to understand the overall building design, please do get in touch with us. You can drop us an email and we can help you with your projects. And the reason there's no one answer for all projects is that all of you will be using different tools. You'll have geometry in different formats. You might be using different building simulation tools. So exporting to those tools, it will vary a bit by tool. So one tool might have a different way to get the wind pressure coefficients in. Another tool will have a slightly different way to do it. So please do get in touch with us, and we can guide you through that. And look, this is a good time. A lot of us are working from home. Perhaps you never had time to look at this, when you were maybe more busy, and there wasn't scope to look at that. But hopefully, if you work from home, you might have a bit more time. You're interested in doing this. This would be a great learning, and we can do this together. We can help you with your projects. Okay, we have another question, which is, do you have some academic support? We do. We have an academic partners program. Yes, you can email at encarn@simscale.com and we can give you more information on that. We have a colleague who deals with partnerships with universities and academics. If there's no other questions, I think what we'll do is feel free to leave if you need to. If there's any other questions coming in, I'll stay on the line a few more minutes and answer them. Feel free to drop questions on the chat or email us, and our colleagues at SimScale will make these slides available in the next few days. And please follow our SimScale LinkedIn channel as well. We're always posting blogs and updates on our LinkedIn channel. And again, just to summarize, pressure coefficients of building facades, absolutely critical when it comes to designing buildings. So please do get in touch with us if you're interested in more information on that. Okay, we've got another question. How does SimScale take in account different climate data? Fantastic question. Thank you. Thank you, Federico. So we can import a windrows, and what that means is we can take in the annual wind data for any location, so wind speed and wind direction, and we also have a database connected to SimScale. So if you're in SimScale, you might remember Darren showed one of the steps was define windrows. You can just in the SimScale platform enter the location. So for example, if the location is London, in the windrows dialog box, you just type in London, and then it's like searching on a map, right? You can put in a postcode, for example, or a city, and then you click on London, and then the data is populated automatically. So the windrows for London would automatically come in, and you also have the option to import your own data as well. So we give you both options. We have the weather database there for you, or you can import your own data as well. And we also have, you can customize the data as well. We've got clients customizing manually imported data to look at seasons and the difference between seasons, and that's very easy to do as well. Okay. Yeah, so wind intensity and direction. So I've just answered that question. So that is very location specific. So we'll bring in weather data for a particular location, and we have the weather database connected straight in SimScale now. The question on fluid structure interaction, I think Darren answered this previously. So at the moment, no, but we can send you more details of what we can do. Alternatively, if you have a specific problem you're looking to model and simulate, get in touch with us, and we'll be able to advise you, with some more specific, with a more specific answer. Okay, keep the questions coming in. We're happy to stay on for a few more minutes and take your questions. Or if it doesn't have to be a question, to tell us something about the industry, maybe a type of project you're working on right now. It'd be great to hear what's going on. We talk to a lot of people who work on all types of buildings, high-rise, domestic, industrial. We've got people modeling huge master plans, urban layouts, urban designers in SimScale. That works really well. Just an idea of what SimScale can do. So we have a automated PwC tool. PwC stands for pedestrian wind comfort, and it's all transient analysis. What that means is we're modeling a real-time wind, and we can take in, if you imagine a building in a city center with a 500-meter radius around it, including all the context, we can drop that in, bring in the windrows for the location it's in automatically. Literally take 2 to 3 minutes to set up a simulation, hit run, and you can choose how many wind directions you want to run it for. It could be 16, 12, 8, 4, 2, or even 1. And within minutes, you can start getting data out of it. We've done a previous project we did, a city center. I think it was 4 wind directions. We're getting results out in 15 minutes. And because it's transient, it's dynamic, you get some fantastic animations coming out of that. So you can see the airflow around the building. You can see a slice through that building as well. And it's really great because you get the quantitative data as well in that. So I think what would be really interesting for me is to see the treatment of wind pressure coefficients really increasing dramatically in our industry when we design buildings, and SimScale is ideally placed to help you with that. Let me quickly take a look if we have any additional questions. Okay, I can see a few familiar people, attendee list. It'd be great to hear what kind of projects you're working in right now. Okay, I think we will wrap it up there. I'd like to thank you for everyone for joining this webinar and joining SimScale. Stay safe. These are interesting times. Please do get in touch with us how we can help with your building projects. We're here to talk through the different simulation and modeling capabilities SimScale has on the cloud. And we look forward to hearing from you. Thanks again for joining, and we'll call it a close right here. Thank you.